Thanks a lot for the introduction, and thank you for inviting me here to this beautiful campus. It's my honor to make a presentation here in this such a national park like area. And I used to graduate from Professor Gina and Professor Shin's group at Notre Dame. From there, I learned GaN nitride. And today, I would like to share my experience about the GaN technology development in my current company, Qorvo. And here's my I thought, because most programs I'm managing is under either control, I feel a little bit sorry, I cannot talk too much about details. So you might not be able to hear a lot of numbers or those details from my talk. But even I talk about that, maybe a few days later, you won't remember these details, right? So, but I think more important thing is I want to share with you a personal view from industry angle to share with you how technology is developed and why we are going this way, why we are looking at these areas one after another. Hopefully this will help you to develop your future career path and decide what area you might be more interested in looking at and how you want to spend your time more efficiently. So, okay, here's an outline. Basically, I will give a brief introduction about Qorvo. I will tell you what we are doing there and what we have in our past, what kind of gallium nitride technology nodes we have developed. And some programs we are focusing right now. For example, the Stereo 9 program, we are trying to mature the technology of our 19nm W-band GaN device there. And you might be hearing something a little bit different from what you are doing daily, like what from an engineer point of view, what is important to us compared to what you might be learning here. You are doing a lot of pioneering study here, which is great, and how we want to connect it with our real life. That is what we are focusing on. And at the end, I'm also going to talk about some future technology building blocks we are working on and how I may look at these building blocks, how we want them to be incorporated into our existing GaN systems. Okay, yeah, so a busy slide. Qorvo, we are working on multiple different areas from the IoT to 5G. These are commercial areas, and for military defense, we are also working on that. We are serving different prime contractors and as well as a lot of, for example, you have a smartphone, there are Qorvo products, HBT-based power amplifier, as well as BAW filters inside. Qorvo is a listed company in NASDAQ. We have more than 8,000 employees globally, and we view ourselves a big player to help us to connect all the components in the world. That's I would say the connectivity is what we are focusing on using our RF technology. Okay, and we are developing technology for dual use, meaning we are working on commercial side as well as defense side. This is very important. Here is the logic behind the technology development. Most of the time, we leverage government funding and or internal funding to develop the most advanced technology nodes. It will be used for defense applications first, and then we rely on our high volume production to lower the cost so that it will flow into the commercial area. For example, a lot of GaN technology we developed for defense applications have been used for the baseband for 5G nowadays. And for mobile phone, it's the same thing. From our old days, we have the gallium arsenide technology, and nowadays we have GaN technology. Especially for mobile phone, I would like to mention, we are also developing a lot of BAW filter technology for high frequency use. And a lot of technology nowadays is still also used in the defense applications. So we call it dual use technology. This business model will help us to lower the cost for product development as well as production in the future. Okay, here is our foundation. We have all these process technology listed on the left-hand side. We have for gallium nitride technology, we have 19nm gates all the way to 0.5 micron gate. They represent different frequency applications as well as power ratings. And for gallium arsenide, we have the HBT and PHEM technology. We are working on BAW filters, SAW filters for mobile phone application. This is a very huge market. And we also have, a lot of people are not aware of that. Qorvo is also actually working on silicon technology, but we are fabless in that sense. We have designers focusing on IF, CMOS, as well as SOI technology. They are working on sensors and IoT applications. Very recently, we started to offer foundry services for advanced packaging. So here you can see I list our system in packaging capabilities here. We have the multiple chip module level packaging and QFN, all these type of packaging, different platforms. We are focusing on wafer level packaging as well as package on package, chip on chip. This 3D packaging, which is related with the heterogeneous integration nowadays. It is a very hot topic. I will cover it a little bit. And we are SHIP program performer. I will have an introduction for that in my slides later. And by leveraging the high volume production, we can effectively driven the manufacturing costs low. And this is very important for us. And we are shipping like more than 10 million devices every day. Okay, this is another busy chart. I don't expect you to read everything here. You can look at it later. But this is mainly for defense or satellite applications. But you might be telling for all the connectivity related or communication related IF technology, Qorvo is playing a role there. That is how we view our strength is for different frequency range from DC to W band or even higher frequency range for power amplifier, low noise amplifier. And the final users, especially for this defense area, could be these technology may be used in the radar system or EW, electronic warfare. And the communication, especially for nowadays, the radar system require multifunction, not only for detection applications, but also want to add the communication function into that. And we are developing all kinds of products in these areas. And this is the major area that my division, the high performance analog division, is focusing at. Okay. And for our foundry services, Qorvo has been supporting our defense for over 30 years. And we offer open foundry services for university. DIB means those prime contractors like Lockheed Martin, Northrop, Raytheon, etc., and as well as small business companies. We are the largest foundry for 3.5 compound semiconductor in the US. And yeah, as I mentioned, we are trying to drive the cost low, leveraging our high volume production here. Okay, so finishing the introduction for Qorvo. So let's go to the next part. What is the trend for technology development? How you build? I know you are working on different projects. Everyone is so excellent, and you might want to develop all kinds of world record, right? Looking at each, you might want to develop the fastest operating devices, which are offering the highest power or most sensitive sensors. But how we decide or how we know where the technology will go. So if there is only one message I want you to bring home of this talk, this might be the one. Just take a look at this so-called SWOT. I always use this as a standard when I make a judgment for technology to decide if I want to spend time on this topic or not. And the SWOT is an abbreviation. S represents size, and the W represents weight, and the P represents power, or sometimes power density. The reason we are talking about this is we always want the size, no matter if it is chip level or system level, we want it to be as small as possible. We want the less to be as less as possible. But at the same time, we want more power from it. Or you can take it as without increasing the size and weight, we want to increase the power or the power density in that sense. Sometimes people will add another letter C at the end, called swap C. C represents cost. And this is pretty important for industry, especially for company. If you want to survive, you have to make money, right? If you are not profitable, how can you make a sustainable path to keep innovating new things? So we need to get the cost down. Sometimes it might be at the device level or chip level, but sometimes we maintain the cost at the chip level, but adding more function into it, helping our system players to lower the total cost at the system level. So looking at, don't just look at the cost at one layer structure. It can be multiple layer. And sometimes the technology itself may not be at low cost or may not be very cheap nowadays, but looking forward, following the trend of the materials, for example, like silicon carbide, the substrate cost has been dropped down so much. And there will be some niche market to appear first, and later the system guys will thank you for adopting the technology you developed on this platform. Okay, all right, yeah, here's a quick map for Qorvo. We have different sites across the United States, and our headquarters is in North Carolina, and our gallium arsenide fab is in Oregon, Hillsboro. In Bend, we have our filter team there. They are mainly working on defense-related filters. And in Texas, we have actually two sites. I'm from the Renner site, and where our foundry service, all the equipment is from. And we also have a Campbell site. We have a lot of excellent circuit designers and testing people there. If you are looking at the GaN technology development and maturation, it all happens in our Renner site in Texas. It's very close to Dallas. So if you get a chance to visit Dallas area, yeah, maybe you could come to visit us as well. Okay, here I'm listing all the technology nodes we are offering foundry services to external partners. And yeah, I'm showing a very simple schematic structure for GaN HAMT. We have barrier, we have channel, we have substrate, we have gate. It's 3-terminal devices, very simple, right? But what I want to look at is only the gate NAND, which I marked it here. We are trying to shrink the gate NAND from 0.5 micron, for example, to 90 nanometer. The reason is we really want to drive the device and have it work more efficiently in the high frequency range. We are not only shrinking the gate length, we are also lateral scale down the source string distance and adding other components, trying to reduce, for example, the parasitic capacitance as well as parasitic resistance. So by looking at the chart here, with the reduction of gate size, we are increasing the operating frequency range for these devices, but they are also targeting a different power rating for sure. With the larger gates, the device is more robust to operate at higher voltage, which can offer even higher power. And but once you need high speed, we have to go down in this path. Here I also label the status of different technology nodes. The FRP means full rate production, meaning we are working on this with a high volume production, and low LRP means low volume. And for 90 nanometer gate, which we marked as GaN 09 here, they are in the development stage, and we have a program called Starry Night. We are trying to mature this technology and release it to production. I will talk about later what you need to do once you have a technology demonstrated in the lab and how you mature it to a full production. Okay, why we are going to high frequency? Here I'm listing several application areas. For example, the satellite communication is in the outer space. There is no media in the middle, so it's a very ideal environment for high frequency communication, for W-band or even D-band in the future. And for electronic warfare, going to high frequency will avoid yourself from other interference from your opponent, and basically the noise level is cleaner in that region. And it's also make it harder for your enemy to intercept your signal. That's one reason we are looking at this high frequency range. And for 5G, for sure, nowadays we may not be using W-band or D-band in the base station system, but there is a backhaul, meaning when we transfer our signal from our cell phone to the tower, you always desire higher data rates, and high frequency communicating in that part is needed. And for 5G, if you look at the whole 5G spectrum, it go all the way up to like more than 70 gigahertz. That's also one reason we are looking at high frequency. It will give us higher data rates to allow you to streaming, for example, video at much higher resolution in the near future. Okay. And talking about the technology developments, as we are going to—
May I ask a question?
Sure.
In the last slide,
Yeah.
I wanted to use this question to maybe also remind you, maybe speak a little louder for the folks.
Oh, yeah.
Standing in the back or sitting in the back. If you have to place the airport communication system frequency, as we recently know, Newark and Denver airports both experienced disastrous situations. Where will that frequency be, and where will that power level be?
Well, that's a great question. I think first of all, I will recommend to use Qorvo products. Actually, I should have mentioned that for these frequency ranges, actually a lot of bands are already occupied by military use in the US. It's less available for commercial use. But for airport, it's kind of a special region. And for sure, we would like to have the frequency to be as high as possible. And if you can use GaN, I cannot think of other reasons why not. The GaN offer the highest power, and although the power consumption is one thing people worrying about, because when you are going to high frequency, the efficiency is lower. But for short distance communication, especially for airport, I think GaN is preferred technology nowadays. And but we may not be going to D-band immediately for a lot of, for example, our GaN 15 technology node, which is covering the K-band or any frequency below that. That should be pretty good for communication use for airport. But talking about that, I think it's not only depending on the hardware or infrastructure. We may also need a better software or management system for that to help the GaN technology or hardware to release the full potential of that. Actually, I may cover that a little bit in a later talk today to see how so-called AI will help us. Yeah, but thanks a lot for the question. Okay, looking at the GaN technology development, it's just similar to CMOS, right? You want the device to be smaller and smaller, but for RF, it's also different from CMOS, because CMOS, you always work at the devices working at low bias with low power consumption. You don't need very high current, very high voltage to deliver high power. It's just logic. You just need 0 or 1. We don't have to amplify the signal. But for RF technology, what we really want to do is we see a very small signal coming in. We want to amplify it, make it more noticeable to our system. That means you need to supply more power into this black box. This is much, much more power consuming compared to CMOS technology. That's also one reason. If you go to too small device size, heating will be a problem. Okay, and the next problem will be the efficiency. For example, when we are going to a W-band, more than 100 gigahertz regime, at device level, you may still get a device with, for example, 27, 28% efficiency. But when you integrate it into circuits and add it into the subsystem module, the efficiency could be only single digits. That means more than 90% of the energy incoming into your system turning into heat. So heat management will be another important topic. So everything is correlated. It's not only like it will be great so long as I can invent the fastest GaN in the world by going to the smallest technology node. And it's not. There are more things you need to start worry about later. Okay, so we are now releasing our GaN 09 technology later this year, hopefully in October. And we are also working on the next generation GaN technology here. So this is just to give you a forecast to see how the, for example, in the plot left, the frequency, how frequency increases as the gate keeps shrinking. And on the right-hand side, we are the y-axis, sorry, the font is too small. The y-axis is the power density I'm listing here. And the x-axis is the FT, basically how fast the device can work. Yeah, Mohammed.
So the technology has like multiple metal layers, passives and stuff, or just the transistor?
Qorvo is using, we call 3MI technology, 3 metal interconnect technology. We are building the capacitor, resistor on chip together with the GaN transistors. So we have all the devices passivated with silicon nitride, for example, and other dielectrics for better reliability, for better power performance. And we are also looking at new capacitor technology or introduce new technology like back-end line, such things.
So how about inductors?
Inductors, we have, well, for high frequency application, we want to avoid inductance as much as possible. But it's possible to build the micro inductor if we need, like for example, the transmission line, they will introduce inductance. Yeah. Okay. Here is a TM image for the 90nm gate. This information actually was released a couple of years ago. This is from my previous talk at IMS. For example, we are developing different type of technology for this 90nm gate when we call HV, means high voltage. You can see it's just like a little bit of field plate here we added to the gate. It'll help us, our device, to reach high breakdown, which can deliver higher power, output power. But you're paying the expense at a lower frequency because it also introduces extra capacitance. For example, gate source capacitance, gate drain capacitance. And later, in order to get the device working really in the W-band region, we introduced the T-gate process. And I know that this is not something new in universities, but how to make it reliable, how you can make sure every device looks exactly the same across a 6-inch wafer. We pay a lot of efforts on that. And with the T-gates, we were able to get the FT cutoff frequency about 100 gigahertz. And nowadays, these are just the prototype, like what we realized in our lab. Nowadays, we are trying to mature this technology to production level. That means we need to improve the reliability to have the mean lifetime at least 10 to the power 6 hours. So by going there, we are paying some cost, and I will cover it later. Here are some quick view of the device performance. Maybe some of you will be interested. The IMAX is about 1.4, a little bit less than 1.4 amp per millimeter, and the GM is close to 700 millisiemens per millimeter. And the FT at lower bias is a little bit higher than higher bias. We could reach like 115 gigahertz with Fmax to 60 gigahertz. The really nice thing is we were able to achieve like Gmax, the gain at 9 dB at 94 gigahertz. This is a pretty high gain. And here are some large signal measurement results. And the one thing I would like to point out is the PAE, meaning the efficiency, how efficient your device can work at, is power added efficiency. For sure, it's the higher the better. But once we are going to small gates, this number keeps going down. And the power gain, well, if you look at here, this orange line on the left-hand side, we call it like small signal gain because the input power level is low. But once you are reaching the highest power, this gain start to decrease, partially because of the heating issues. The device will self-heat it. And the power gain typically could be like 3 dB or even more, lower than the small signal gain here. And yeah, basically I'm showing the devices, the same device mirror at different frequency range. At 35 gigahertz, the PA is high, but when you go to the 94 gigahertz, as I mentioned, the efficiency decreased to 27%. But typically we don't expect the output power, maximum output power to change a lot. So at lower frequency or high frequency, the total output power should stay about the same. Okay, and yeah, here are just more results for the different load pool on the device. Okay, just plot them in another way. Okay, now let's talk about how, since we already have this prototype of technology, 19 nanometer devices fabricated, even we are cherry picking the device, showing you the best result, how we can make it more producible in a later stage. So cost is playing a very important role here. If the yield is pretty low across the whole wafer, you are facing a very high cost when you are going to do production. So what I'm going to talk about is all about cost lowering, what we are doing to do that. Okay, here is an overview of the Starry Night program. This program consists of about 4 different efforts. I'm going to introduce maybe 3 of them. The first one is we are trying to expand our platform from 4-inch to 6-inch to make this process more manufacturable on 6-inch silicon carbide wafers. And the 6 silicon carbide wafer is thinned down to 2 mil, that is 15 micron thin. This is mainly for W-band application because once the substrate thickness is too large, you will get extra substrate modes and extra loss with these microwave applications. And we're also developing a structure called AIC. It stands for Advanced Interconnect. And that is something, I have some image for you later for the copper bond structure, and we are developing that. So this program, I think we won this program in late 2021, and we are trying to release the technology later this year. So you can tell it takes about like 4 or 5 years program to mature a technology. This will give you a good idea like how much work is needed by the first look to a program. Okay, and for this 19 nanometer technology, this is what we offer. It also partially answer Mohammed's question. We are having the 19 nanometer gates, and we have the regrown ohmics. The sheet resistance of wafer is typically less than 300 ohm per square. And we have this so-called 3MI flow. And especially in order to reduce the inductance, instead of increasing it, we introduce this individual source via ISV. In the past, when people make these devices, we always put the source connection pads on the side, both sides of the devices, and all the source pad is connected, routed to the side, and then there is a via connected to the backside of the wafer, which is grounded. But in order to work with these high frequency devices, we have to shorten these paths as much as possible. That's why we need to place these individual vias among different fingers, because once we want high finger from these devices, once we want high power from these devices, we need multiple fingers to increase the device width, effective width, to generate the more power. But as we have more fingers, it's harder and harder to connect these fingers or ground those sources facing in the middle of each finger. That's why we need via to locate just between these fingers to get them connected directly to the backside metal. So these via, compared to a silicon world, they are at a pretty much larger size. Silicon, you may be looking at micron or even some micron size right now. And but for RF applications, if you go too small with those size, it actually will increase your inductance. And that is also another area we want to avoid. It also does not, well, having a relatively larger source sphere, it will help the heat dissipation actually, sometimes to help the device to be balanced better across the whole wafer laterally. Okay, and we offer open foundry services. We have the PDK available. If circuit designers want to use it, you can contact us. Okay. Okay, here is the size for AIC. On the right-hand side, you can see the so-called copper bond. It's a very small, but with high aspect ratio copper pillars. Why we need it? They are mainly used as electrode or connectors between different chips. If you want to have one chip sitting together on top of the other one, just imagine you have the copper bond fabricated on the bottom chip, and on the top chip you have the via. Right? They can just sit into each other and form connection directly from the backside. And we also developed the technology called hot via, meaning we will have these copper bond to deliver RF signal or DC signal through these vias. They are not only operating as a grounding connection, but they can have active signals going through them. And in order to be bonding them together, you also need this so-called BBLP. It's actually a landing pad, a backside bond landing pad, to have the copper bond in touch of this pad, and then you can fuse them together. Okay, and we are also maturing this technology for both our 150 nanometer gate and 90 nanometer gate in this Starry Night program on 6-inch wafers. That means we need to offer high volume production of this heterogeneous integration technology before the end of this year.
So can I have a question?
Sure.
So do you also integrate this on standard CMOS chips?
Not yet. Yeah, it's a great question because as I mentioned, the CMOS is using a much smaller pitch size for these interconnects, and we have to work together with the digital people to redesign the layout on those CMOS chips in order to put them together. But we do have plan to bring everything together in the whole chip.
So if the pad on the CMOS is like 75 micrometer, you can do it?
Oh yeah, that's true. Yeah, we basically these copper bond are mainly for RF use. So if we want to transfer the digital signal from, for example, a digital chip to a RF chip, we need to some co-design, so-called, with those guys. But there is no problem in transferring the signal from a layer below to the top layer, and we can even keep adding chips and have the signal going through those so-called RDL layers and going to top.
And the thickness of the GaN chip is like 50 micrometers?
Yes, 50 micrometers.
So have 50 micrometer on top of the CMOS chip if you can do the integration?
Yes, we can do the heterogeneous bonding, or we can have the digital chips on the backside. But depending on the application, if we are making power amplifier, it generates a lot of heat. Maybe you want a heat sink to be close to the GaN chip immediately. Okay, here is a chart like telling you how we start the program at Qorvo at the research level and start to mature it. Every technology has the lifetime. So on the bottom line, we are calling some AD program, advanced development process. If we have some idea, just like you're pitching government or like a student pitching a professor, if you get some new idea, you have the concept stage and you need to do a lot of homework, research study, benchmark to validate it, and then make a good plan, how much resources you need. And then once your boss agreed, everyone put in the effort here, execute the plan. And if there is some good result coming out and the company decided to turn it into a real product, and the result from this AD program will go into the TD process. Sometimes the technology start from the TD process immediately. If we have some pull from the customer say, okay, we want this technology, and we see this can be done without too much effort, and we can start the TD project. So it also starts with the concept stage, but as you go all the way from left to the right-hand side, you can view it as a process. The technology got invented, matured, and go to high volume production, and it might be very welcomed by the market, but as time goes by, the technology itself is no longer applicable, and the volume will ramp down, and by the end it will stop by itself. So it's just a natural process for technology. Yes.
What percent yield is needed for it to be production ready?
What
Percent yield?
Oh, yeah, it's a very good question. Do I have numbers there? No, I don't. Okay, so for high volume production, typically we are looking at yield at different stage. I do have a slide later here during the wafer process, but the end yield, for example, if it is 50 or 60%, is acceptable at the entry level. You know, once you have the technology demonstrated on this whole platform, but eventually we really want the yield to be above 90% or even higher. For example, when I work in the epitaxy world, we always like the yield to be like 95% or even higher for our epi wafers. But for device process, it's more complicated because sometimes the wafer may break during the line, and even the wafer came out intact, you may still have device not working at different level, DC level, RF level. So we are looking at the yield at different levels. Yeah. Okay, and here are two terminology words you might hear in the future if you want to go to the industry or stay in the academic. One is the TRL, technology readiness level. And basically from level 1 is, or you can view TRL 0 as something totally impossible. Okay, and TRL 1 is like you are having some new idea, either at the material level or device level, and you really want to push it. And along this path, you develop the technology, make a good device, and you want the circuit people to use it. So you have circuit designers make a circuit that will increase your TI level to, like, for example, 4 or 5. And you want to contact some, like either Boeing or Lockheed Martin to put your chip into their lab to do a field test. It increase it further down to the subsystem level development, for example, TIL 7 or 8, and eventually it goes into their system at the production level or accepted by the whole system. An easy way to look at this TIL level is what I think is just the technology got developed and validated at different levels. It's going higher and higher, right? With more and more people involved at different levels. But for MRL, manufacturing readiness, it's a little bit different because everything here we are looking at how feasible this technology is to make it happen in a production line. It also starts with a very fundamental stage, like concept stage, but later we are looking at, for example, demonstrated in the lab environment, like maybe from 1 to 4 level here is about the same as what we are doing in the school or in a R&D lab in company. But beyond that, we are looking at how we can, for example, save the sources, lower the cost, make the process more controllable, because industry does not like surprise, right? Unlike universities, surprise is always good. That means you can have another paper to write. But in industry, we want everything to be controlled, and we want to do all kinds of corner study to make sure we will stay in the center of the control chart. So for MRL, as the level goes higher and higher, that means the production is going to higher and higher volume. And for sure, the process is more and more sophisticated. Okay, I'm showing a table that we are using daily, how to control or help us to get to a better or higher MRL level. These are the things we are looking at. We need to make judgment if we have enough process capability as well as process control if it's there. For every task here, we have people, we have owner for these tasks in the company to control it. And also we need to do the failure analysis and see the every process step. We need these documents there, and starting material as well as what kind of parameters we need to characterize after each process step. We have to make sure every step is going towards the direction we would like it to be, and also reliability. This is another big topic. And the EDA, if we have the EDA tool, the design tool ready for offering this foundry service or go to production, and if we need to introduce any special process, because in company, the process is always introduced at a module level. It's not like a single step. We actually package a few different steps, including inspection, into a module. Once it's determined, we use it as a fixed step. Our engineer can insert it easily into different process flow. So we need to inspect if any new tools or new processes needed, or these modules needs to be modified, and what customer impact will be. If there will be any new impacts caused by this new process, we need to know that. And here are some SPC charts we are looking at every day. You need to run like 50 or even 70 wafers to establish such a chart. For example, we are showing a source string, recess, edge. This is for ohmic process, regrowth process. You first etch the source string area down for a certain depth, and I'm showing the scale depth here. And across the whole wafer, you measure the uniformity, and you just keep the same process for multiple times, and you establish this chart, and you define its upper limit and lower limit, USL and LSL. And based on the statistics result, you calculate the CPK. You can view this as a number to show how repeatable or how well you can control your process. The higher the value, the better. Okay, and basically we are repeating this process for almost every step. Like when we are making a gate for the device, we measure the gate resist. We call CD as meaning critical dimension. We use, for example, SEM to measure the gate width or the gate length for every devices, and we create this chart. If the photoresist process goes something wrong, we will know it from here. And the contact resistance is what we measure from our inline DC measurements. During the wafer process, we have multiple characterization steps in the middle of the process. Once we have all these metal pads fabricated, you go to measure these DC, sometimes we measure CV, right? So all of these things need to be shown in this SPC chart. Okay, and there are other topics. Sorry, I'm running over time. For example, the yield. We have yield defined at different stages. When wafer process ended, you have to count how many wafers survive through this run-out process, and if the DC measurements pass the standard, or you even have the final visual inspection. So basically, the product of all these yield numbers lead you to the final yield from the production. And the reliability, as I mentioned, we need our device to survive for 10 to the power 6 hours at 200 degrees C channel temperature. This is a very stringent condition, but sometimes we will get a good surprise. For example, some of our 90 nanometer gate devices, the lifetime is much longer. And you also need to come up with cost model for every process. You need to know how much money you're spending on each step, spinning, photoresist, or PECVD deposition. So everything needs to be break down into details. Okay. All right. And another understanding from this swap C is, my personal understanding is you always want to get more from less, meaning without increasing the size of the chip, you want to get more functions or more higher data rates. This is one quick example. We used to develop some so-called self-bias circulator technology. So long as, since we already have a good device to work with, and we want the circuit people to adopt this technology to make a mimic, right? So this is how we use it. We can have the GaN device going to the RF switch here. It can operate as a switch on and off. And it will also go to the transmitter as a power amplifier to amplify any signal from the right hand from the signal coming from the left hand and go to the antenna on the right hand side to get emitted. And for receiver, we can have the LNA, no noise amplifier, by looking at the small, very weak signal coming from this antenna and amplify it and to have our baseband process the signal. So, but looking at this switch, it can be either on and off for every route. That means once the transmitter is working, the receiver will stop seeing signal from the antenna. How we can enable both party to work at the same time, that is the unit we need called circulator here. In circulator, the RF signal can only go in one direction. So in this case, the signal go from transmitter through the circulator to the antenna, and it won't be leaking into the receiver side. And so the receiver will only see the antenna receiving signals and pass it along to the receiver itself. It won't see the transmitter part. And in the past, for example, these are some images for the circulator commercial product you can buy from the market. They're typically pretty bulky with these metal cases, and they are heavy. So without increasing our chip size, how we can integrate this function into our GaN MMIC, that is one thing we are interested into it. So looking at the inside of these circulators, it's pretty simple. You have the metal line, the three-way metal line, metal pads there, and then you have a ferrite material, which is a dark material at the bottom, and you have a pretty big magnets, permanent magnets. It's very bulky on top to supply magnetic fields vertically. A lot of room comes from the metal casing here, as you can see, and as well as the top bulky permanent magnets. So in order to shrink this size, make it integratable with GaN MMICs, we have to get rid of this bulky stuff. So this is our approach in the DARPA M3IC program. We try to etch a pocket on the backside of our silicon carbide substrate. The substrate is thin down to 4 mil, 100 micron thick. We are using this technology together with our GaN 1.5 technology nodes, which is 150 nanometer. Oh, sorry, 150 nanometer gate. So the substrate thickness is 100 micron there. We fill in this self-biased material. That means the magnetic field will sustain itself without needs of these permanent magnets outside. These are some new material Argonne National Lab and metamagnetics developed for different frequency ranges. We incorporated that these material into our structure, and in this way we can fabricate the whole GaN circuit. For example, we have the PA and LNA fabricated on the same chip. Okay. And we were able to make some C-band self-biased circulator. In this way, the material is from Argonne National Lab. It's based on nanowire composite. Basically, you took AAO templates, porous, and you do electroplating of cobalt or nickel, iron cobalt or iron nickel nanowires in these AAO templates, and magnetize it once in a strong magnetic field, and the magnetic field will stay there. And you insert this piece of disc into the backside of the GaN MMIC. And the disc size, because it's lower frequency, the disc size is relatively big. It's 5.8 millimeter. It works well in the C-band, although the insertion loss is still a little bit high, 2.7 dB. The material still requires some further maturation. We are looking at that right now. But the great thing is it can handle 40 watts. This is a very, very high watt. Thinking about how much heat it will generate if you have 40 watt, from your device, and especially for defense applications, it offers great opportunity, I would say, in the near future if we can incorporate it into our reader system. And for K-band,
before we move on, this is Jim Huang. I think the isolation of 15 dB may not be enough.
Yes, I agree with you. Yeah, you're right. That's why we are looking at optimizing the material itself and see how we can further improve it for the C-band application. And sometimes it also depends on the design. We had some difficulty in getting a very good consistency of the material from batch to batch. That's also why we having it in a production mode is very important to have a consistent material supply. But yeah, I agree with you. Our target is to get at least 20 dB isolation with these devices. Yeah, and if you look at the K-band, the isolation is much better here. Yeah, we were able to get like 26 dB, and the insertion loss is below 0.5 dB. This is largely because the material itself is more matured. And the power handling is also great. So it can handle like more than 6 watt power. Okay. And by using different design, you can have a narrow band and a broad band. I'm showing 2 cases here. On the left-hand side is a narrow band circulator, and the left-hand side, it covers like 10% bandwidth of the operating frequency. It's a broadband one. Okay. And
so can
yeah,
you
sure.
go to D band here? Have you tried?
D band, we never try. We have W band.
Okay.
Yeah, we were able to go to W band, and using the same material here, the result is pretty good. But that was demonstrated in the phase 1 of DARPA M3IC project. And when we are going to the later phases, DARPA want us to focus on K band only and C band. Yeah, so that's why
it's up to like 100 gigahertz. Right?
First of all, it's possible. It's doable, and you just need a smaller size of the discs. This might be like 0.5 millimeter.
So maybe the material itself like might resonate or something like that.
Material quality has no problem. I think the major challenging is with the process. For example, when you cut the material, how smooth you can have the edge to be is largely related with your insertion loss. And if you use laser cutting, for example, the heat generated by the laser, it overburn the material and also increase the loss. So we paid a lot of attention and worked a lot on how to reduce the loss when we incorporate these discs.
And have you looked at cryogenic temperatures?
We never tested it there, but we do have the devices going through high cryogenic temperature, and yeah, we can see some improvement in the performance by going through that process.
I also want to ask a quick question on the circulator.
Yeah.
On what is the percentage of the, because eventually what you wanted to do is you wanted to go through the Faraday rotation of the electric field.
Yes.
You have the electromagnetic wave.
Yeah.
And then I don't really know what you're using here, like the CDW or microstrip.
Yeah.
So you have your electric field in your
Yeah,
RF transmission lines, and then you want your electric field to overlap with the magnetic material as much as possible in order to reduce the amount of electrical length. In order to actually rotate the electric field, you want it to rotate.
Yeah.
I forgot, it's 45 degrees or 90 degrees. Yeah, 45 degrees, maybe one way, another 45 degrees this way. That's how you isolate them, right? Because polarization, isolation, depending on rather, isolation depends on how well the polarization are perpendicular to each other or slightly off from the 90 degrees, right? So that's why I'm asking, what is the percentage of the electric magnetic wave are inside the magnetic material? And what is the loss division between the metal and the magnetic
You know
material?
how much it got leaked out.
What is
Yeah.
What is the loss in the metal itself? What is the loss either leaked out or consumed because of the finite loss?
It's a very good question, and maybe the next slide will
Answer the question.
So in one more, this one may answer your question.
Yeah.
In order to guarantee a good alignment, first of all, we need to have the disc integrated very, how to say, the pocket first of all, the pocket we etch need to be very smooth with the bottom, and the disc need to be very flat. And they need to go in a very, very parallel way from the circuit on the top, right? And then in order to guarantee we have the magnetic fields very uniformly going vertically direction. Typically, we have the pad designed a little bit smaller compared to the whole disk. So in that way, the magnetic field across the circular, this circle is the metal pad here, will be perfectly vertically aligned. So yeah, that if it is not aligned very well, for sure we will see higher insertion loss very easily. Yeah, hope that answers your question. Yeah.
What was limiting your isolation to be 15 dB?
It's I would say it's a trade-off between the, for example, bandwidth. It is largely depending on the design. So if you want a broadband, typically we see a worse isolation. But if you can keep your band as narrow as possible, the isolation can be pretty good.
Very nice.
Yeah, and it also depends on how much field. I didn't include the magnetic characterization result here, but it is in our paper published before. You want the a certain remnant field to be there, as well as the okay, let me explain in this way. For example, when we use the nanowire based material, right, you want all the nanowire align in the parallel way. And once you magnetize it, you want all the domain also aligned. You don't want something like looking at different directions. You want the nanowires diameter to be very uniform, distributed, because different diameter will give you somewhere stronger field, somewhere is weaker field. All of these is highly related with the process. And yes, we did a lot of things trying to even modify or customize those AAO template we receive from vendor to reduce the insertion loss. But typically speaking, when we do the simulation, we didn't see the magnetic field got leaked out a lot. A lot of isolation is still mainly caused by how well we integrate what media we put between the magnetic disk and the silicon carbide in the pockets, how we fill the gaps, and how big is the gap. All of those trivial things, actually, they really matter. Yeah. Okay, and looking at the size, I'm plotting our size, device size compared to a commercial product. As I mentioned previously, we really want the size to go down, right? And we were able to reduce the size by over 100 times. If we are going to the system level, the size actually got reduced by more than 1,000 times. Okay, here is the final circuit we fabricated. And we can have a good device, but you always want someone to adopt this technology. That's why I mentioned only by developing a good device may not be enough. And here we integrated this K-band circulator with our PA and LNA. And we have all the small signal and large signal measured. And probably I didn't include the LNA data here, but I do have that. And the chip size is pretty small. You can see it's less than 5 millimeter by less than 3 millimeter. It's completely compatible with the TR Mimic chips nowadays our customers are using. And you can view this effort as a wafer level integration. And we also have a lot of effort working on chip level integration. I think maybe I'm running over time, right? How much time I may have?
Like 5 more.
5 more minutes? Okay. Yeah, maybe I will jump over this SHIP program introduction. We basically at Qorvo, we are looking at developing all these advanced packaging technology. We are also offering this as foundry services. And I want to go to the next one is what's next? Once we have, probably you feel the GaN technology is good enough nowadays, and why we are still working on it, right? So we are working on different materials. One thing is the unpolar material. You must be very familiar with it. I'm not going to spend too much time here, but we have an Eclipse program, and recently we have achieved some W-band result, and hopefully we can publish it very soon. This, by using N-polar, we are looking at a higher power rating at high frequency. This is one major reason, but it also have a lot of challenges. The first challenge is with the epi material. It's less consistent or less mature with the compared to gallium nitride. So we are working with Renaissance and their parents under this Eclipse program. They are trying to help them to mature their material for these unpowered applications. And this is another program we are working with Professor Gina and Professor Shin's group, Night Rider. We are looking at the scanning natural or L scan. We are trying to leverage our 90-nanometer technology, use this new L scan material to push the power performance in the event to the next level. We were able to demonstrate it, this L scan hand on 150 millimeter silicon carbide wafer. I believe this is the first time people have done that because it's pretty hard to grow high quality material. At least at Qorvo, by MOCVD, we use MBE to grow the L scan. And we have achieved a pretty uniform sheet resistance. After passivation, we expect the sheet resistance to go to 250. And as I mentioned, as you go to higher frequency, you have more and more heat generated. And this is another program, DAPA threads program. We are looking at using diamond to help with the heat dissipation by placing diamond on both top side as well as bottom side in order to get the GaN hand power to meet the goal, like 81 watt per millimeter. This is a very high power, about 16 times compared to what we can get nowadays. So heat issue, thermal issue is I would say the final issue once we go to a higher frequency regime, and because of a low efficiency. Okay. Yeah, here I'm showing some of our approaches. We have the diamond on the back side as well as adding it on the top side. We are working on that. Okay, here might be the last topic I want to share is how we can accelerate the technology development. We used to spend a lot of time, as you can see, those SPC chart control. We need to do a lot of corner study. Like if I change this parameter in our process, how much impact it will generate for our devices, how much deviation I will see from device performance. That is very time consuming and take a lot of time, how we can accelerate it. And another thing is for circuit design. Maybe you might think that circuit design is a simple thing, but in industry, typically, for example, to design a new power amplifier, it takes 3 months for a very experienced circuit designer. And we need another 1 month to help him to check if the design follows our design rule, if it is can fit into our production line to tape out. So, and also, apart from the circuit design itself, developing a new device model is also time consuming. And it takes at least 1 month to develop small signal, large signal, at different temperature, noise, different models. And the bad thing is these models are not related with each other. For example, we have to develop these models at different temperature ranging, at different temperatures, but your device or circuit may work under other temperatures we develop this model at. That caused some deviation in the performance. So we are asking if AI is the solution to help us to accelerate it. And AI itself has its own deficiency or shortcoming. We can talk more about it later. But yeah, basically, I think that's all I want to share with you. At the end, this is my personal interpretation for SWAP. In the future, maybe we want this A to represent AI acceleration. Yeah, so, okay, thanks a lot for your time.